In this video, we'll be building a video generation model based on Diffusion Transformer. Specifically, we'll be looking at this Latent Diffusion Transformer for video generation paper. And after getting an understanding of all the different parts of it and how each of those parts impact the generation output, we'll go through an implementation and see the kind of videos that our model generates. We'll start off with the very simple Moving MNIST dataset. And within that also, pick the easiest set of videos, which have just one number moving across the frame. We'll also select categories of videos from UCF101 dataset and train our model on that. These categories are specifically chosen such that the background for them mostly remains the same. So it should be easier to learn to generate these videos with a model that is relatively cheaper to train. For this paper, the authors used the DIT adaptive layer norm block as the building block for their transformer. So we'll quickly go through that first, and here I'll only cover the most important details relevant to this paper. So if you need to understand DIT in detail, I would suggest to also check my previous video where I have covered it. So DIT works on latent images, and similar to VIT, the first block is the patch embedding block, which takes a noisy latent image, divides it into patches of say height ph and width pw, and then through an FC layer generates a d-dimensional representation for each of the patch tokens, where d is the hidden size of transformer. Rather than linear layer, the same thing you can also do with 2D convolutions. Then the patch embedding block adds positional information to the patch representation, which as we had seen in previous video for DIT, it's 2D positional embeddings using the sine and cosine functions. These patch tokens are then passed on to a series of transformer encoder layers. For DIT, the variant with which the authors get best performance, which is what the authors of this paper also used for their video generation model, is the adaptive layer norm 0 variant, which had a multi-head attention with layer norm and an MLP layer with layer norm. The representation of time step and class condition was added together, and using an MLP, we predicted 6 sets of d-dimensional parameters. 4 of them were the affine parameters for both the layer norms, and 2 of them were scale parameters for scaling the output of both MLP and attention modules prior to residual connection. And during initialization in DIT, the scale values are all set to 0, such that the entire DIT block acts as an identity block at the start. After the last layer, to convert the d-dimensional tokens to patches of latent image, we have the unpatchify block. We convert each token to ph times pw times channel dimension using a layer norm and MLP. And it will be either the noise predictions for each of those input patches or predicted denoised patches. From both these kinds of prediction, we can get the denoised latent patches and rearrange to get our latent image. During inference, we would start with a random noise sample and denoise it for all time steps. And after the final one, feed the denoised latent image prediction to a trained autoencoder to get our generated image. So that was a recap of DIT. Now let's start getting an understanding of all the components of this video generation model. So let's say we have this video. By the way, this itself is a generated video. But let's assume this was a video in our dataset, and it has these set of 4 frames. Since this is latent diffusion transformer, so we'll not be working in pixel space, but rather latent space. And during diffusion training, we would also be adding noise to the entire video. So consider these to be the noisy latent representations of the frames of the video. The authors experiment with multiple variants for the model, but for all of them, the overall architecture is same as DIT. That is patch embedding block followed by a series of transformer encoder layers followed by unpatchify block. Let's start with the patch embedding block. Rather than single noisy image, we are now working with multiple noisy latent images. That is noisy frames from the video. And the unpatchify block is also going to have to generate noise predictions or clean latent predictions for all the corresponding frames. For patch embedding block, the authors try with two options. One they call as compression frame patch embedding, which is similar to tubelet embedding of Diffusion Transformer paper. Say you have these latent images for a video that has 4 frames, and the latent image height and width is also 4. In this variation of patch embedding, we extract representations of non-overlapping tubes of having certain height, width, and temporal size. So assume our patch size is 2 along height, width, and temporal dimension. Then these white lines mark our patch divisions in the spatial dimension. And this marks our patch division in the temporal dimension. Essentially, patch embedding block would be learning to generate representations of these tubes. In implementation, this is how it would look. You have this batch size, cross frames, cross C, cross H, cross W latent frames of video input, and then you are rearranging to get this shape. So rather than our linear layer transforming C times patch height times patch width input to D dimension, it will now transform this to D dimensions, and in process capture representation of all these tubes. If your patch embedding implementation was using convolutions, then now instead of 2D convolution, you would be doing 3D convolutions. The other option that the authors use is exactly same as DIT or VIT. They call this as uniform frame patch embedding, and here we simply apply the patch embedding to each video frame individually. So for example, in this case, where we are working with a batch size of 1, and that one video has 4 frames, the patch embedding block will operate as if we are working with images and our batch has 4 images. So all we'll do in implementation is reshape the input prior to calling our DIT patch embedding block. That's it. So from batch size, cross frames, cross C, cross H, cross W, to batch size times frames, cross C, cross H, cross W. So the patch embedding block just works as if you are working with images with a batch size of this value. Now we also need to add position embedding to all patches in the image. And to handle position embedding for videos, the authors simply replicate the 2D sinusoidal position embedding that we used in DIT along the temporal dimension, which means our positional embedding would still be of shape number of spatial patch tokens, in this case 4, cross D. But for both uniform and compression frame patch embedding, it would be replicated along both the batch and temporal dimension. The unpatchify block of both variations are same as DIT, that is layer norm and linear layer. But for the compression frame patch embedding, we additionally have a 3D transposed convolution layer to upsample along the time dimension. Because during the compression patch embedding, we would have downsampled along the time dimension. For this video, for all the future illustrations, I have used the uniform frame patch embedding, as that is what the authors found to be giving better results. With the patch embedding and unpatchify block done, we'll now move to the 4 variants of transformer architecture that the authors experiment with. For each of the 4 variants, the 2 main components are spatial and temporal attention. So let's take a look at that. Spatial modeling is same as DIT or any transformer based model working on images, wherein given these frames of a video, we patchify each image. And assume we have 4 patch tokens as a result of the embedding block call. F values indicate the frame number, so F0 is the first frame and F3 is the last frame. P values indicate the patches. The position representation will be 2D embedding. Also, I have used these image patches to represent the patch tokens. But remember, each of these patch tokens are D-dimensional tensors that are obtained after the patch embedding call. During spatial modeling, each patch token attends to all tokens of the same temporal index. So as an example, the first frame's patch 0 will attend to all patch tokens of frame 0. Similarly, the first patch token of all the other frames attends to these patch tokens. Since for spatial modeling, we are not bothered by the temporal dimension at all, this is same as treating all frames of video as different batch images. And then everything will work exactly similar to how DIT or VIT handles a batch of images. This is why prior to any spatial layer in implementation, we'll take our input, which will be batch size cross frames cross patch tokens cross D, and here we are assuming uniform frame patch embedding. We'll take this and reshape it so that the first dimension is batch size times frames. So it's as if we are working with images rather than video, and this is the batch size. Now let's look at what happens during temporal modeling or temporal attention. We again have the same patch tokens, but this time each patch token attends to patch tokens of all frames that have the same spatial index. So the first frame patch 0 token will attend to patch 0 token of frames 0, 1, 2 and 3. Similarly, the other first frame patch tokens will attend to these. In this case, because we are now not concerned with the spatial dimension, this is same as treating tokens at spatially different positions as different batches. This is why prior to any temporal layer in implementation, we'll now take our input, which will again be batch size cross frames cross patch tokens cross D. We'll take this and rearrange and reshape it so that the first dimension is batch size times patch tokens, and second dimension, over which the attention will be computed, is the temporal dimension. When we'll see the implementation for this video model, we'll see that this rearrange for spatial and temporal dimension is the only new aspect that we have to handle from our DIT implementation. Rest of the model code is pretty much same as our DIT video. Okay, so with this understanding of spatial and temporal modeling, let's look at the 4 variants. We start with DIT. So these were our layers. And this was our DIT block. Now in DIT, these encoder layers were all working on modeling attention in the spatial dimension. So essentially we can call them transformer spatial layers. And by that we just mean that in this module, the attention was computed along the spatial dimension. Apart from adaptive layer norm DIT block, the authors also try out a different variation for conditioning on time and class. They call this the all tokens approach, where the time step and class representations are just concatenated to the sequence of tokens in the first layer. This is also similar to in-context conditioning that was tried out by DIT authors. But for all illustrations, we'll continue to use scalable adaptive layer norm block, as when we look at results later in the video, we'll see that this performs better than the all tokens approach. All the variants basically differed on how the temporal and spatial modeling was factorized in the architecture. Starting with variant 1. This is a sequence of spatial and temporal layers, one after another. In temporal layer, the attention is happening along the temporal dimension. So after every spatial layer, we'll just rearrange the output so that the dimension at which attention will be happening is the time dimension. For the second variant, we first have all spatial layers and then a bunch of all temporal layers. For the third and fourth variant, the factorization happens inside each transformer block. So all transformer layers will be the same, but the blocks will change. This is the block for the third variant. And let's just leave out the layer norm affine parameters and scale parameters to get a clearer picture of the third and fourth variants block. In the third variant, for the transformer block, we first have a spatial attention module, followed by a temporal attention module, followed by regular MLP. So now the output of spatial attention would be batch size times frames cross patch tokens cross D. And prior to temporal attention, just like temporal encoder layers, we'll reshape it to be batch size times patches cross frames cross D. For the fourth variant, for the transformer block, the layer norm output goes as input to both spatial and temporal attention modules, both using half of the attention heads, designated to the entire block. The layer norm output is again reshaped differently for each of them to ensure that for spatial attention, we work with this shape, and for temporal, we work with this shape. Then we fuse them together, where inside this, all that really happens is that both the spatial and temporal attention outputs are reshaped to batch size times frames cross patch tokens cross D and added together. As a side note, these variants are very similar to different variants experimented by the authors of Diffusion Transformer, where they adapted transformer architecture for the task of video classification. In order to give the model a sense of spatial positions, we added positional embedding to the patch representations inside the patch embedding block. To do the same for temporal positions or frame positions, we add temporal position embeddings. The authors tried two types of embedding for this. One is absolute position embeddings, using sine and cosine functions for all frame positions, like we did for time steps in DIT, and the other one is using rotary position embeddings. For absolute position embeddings, which we'll ultimately use in implementation, we would get a number of frames cross D-dimensional embedding. And to give our model this knowledge of temporal positions, we would take the input, which will be batch size cross frames cross patches cross D, and reshape it to batch size times patches cross frames cross D, and then simply add this temporal positional embedding. We'll see during implementation where exactly this embedding is added. So we have seen many variations of the architecture and variations of components as well. Specifically, for frame patch embedding, we saw the compression frame embedding versus uniform frame patch embedding. For time step and class conditioning, we saw either adaptive layer norm or all token strategy. Absolute and relative position embeddings for temporal embeddings. And for architecture, we saw 4 variants. Let's see the results of different experiments that the authors do to compare each of these strategies. First up is time step and class conditioning. For evaluations, the authors use FVD metric, which is very similar to FID, which we looked at in the DIT video, except FVD is for videos. So for the pre-trained model, we would be using something like i3D, which is a video model, pre-trained on a video dataset. And rather than getting image representations, we would get representations of real and fake videos generated by our diffusion model. Between these two time step and class conditioning strategies, the adaptive layer norm version works significantly better. The authors feel that this is because in the all tokens version, the conditioning input is only introduced to the first layer. So this conditioning information might not effectively be propagated across all layers, as opposed to adaptive layer norm, where it's encoded separately for each transformer block or layer. Next comparison is between uniform frame patch embedding, where we perform patch embedding separately for each of the frames of video, and compression frame patch embedding. Uniform works better, and the hypothesis is that compression frame patch embedding, where we are effectively downsampling in the temporal dimension, this leads to loss of information, which ends up being costly for the generative model, which is trying to learn to generate these videos. Even from model flops perspective, uniform frame patch embedding will have more flops because it would be handling more number of tokens. And like we saw in DIT video as well, flops are a key component for improving performance. For temporal embeddings, both choices are close in performance, with absolute being slightly better. So this is what we'll stick to during our implementation. The last comparison is amongst the variants. Variant 4, where we used half attention heads for spatial and the other half for temporal attention, performs the worst. And that makes sense because, again, going back to flops, this has the lowest flops amongst all variants, being about 1/4 of the value compared to others. The next best is variant 2, which was sequence of spatial layers followed by temporal layers. The authors believe that this division causes loss of spatial information and spatial capabilities during the temporal layers, which degrades the overall performance. The second best is variant 3, where we factorized self-attention within each block across spatial and temporal dimension. This is very close in performance to variant 1, where we have alternate spatial and temporal layers, with each layer having layer norm, self-attention, and MLP. Since variant 1 achieves the best FVD, so this is the variant that we look at in implementation. Just like DIT, the authors train different scales of model. And not surprisingly, as we increase the scale, we keep getting better and better performance. These configurations are also exactly same as DIT configurations. Finally, when we compare this video transformer model on the basis of FVD, it ends up to be the best performing video generation model amongst all other models that were used in comparison. But it significantly gets better result for this image variant. This is more of a training variation rather than a model variation per se. Here, instead of training only on latent videos, which is this row here, we do a joint training of Diffusion Transformer on latent images as well as videos. So for video training, we have frames of a video, and obviously we'll have multiple videos in the batch. In joint video image training, for each item in the batch, that is to each video frames, we append randomly sampled video frames from our dataset. So basically aggregate all frames of all videos and then randomly select n frames for each batch item. Here in the example, n equals 1, so only one random frame is appended. But during training, the authors use n equals 8. During joint video image training, for the video tokens, all layers will be used. So this is our variant 1. For these frames of the batch, which were frames belonging to videos in the batch, for which we need temporal consistency, both temporal and spatial layers will be used. However, for these, which were the appended frames in the batch, only spatial layers will be called. So for all temporal layers, we would exclude the frames not related to the video. And for these appended frames, we would basically be doing a forward pass through a DIT-like model. The spatial layers will use these appended frames as well as video frames to learn to generate images such that spatially they match the distribution of frames in our dataset. Whereas the temporal layers would learn to generate frames that ensure temporal consistency and also match the distribution of temporal aspects present in our dataset, like actions for example. Okay, so now let's look at an implementation of this video generation model. The implementation will be of a base model with patch size 2, but it's configurable. We would be using uniform frame patch embedding and variant 1 design, with each block being adaptive layer norm 0 block that we saw in DIT. For temporal embedding, we'll use absolute position embeddings, and we'll be doing joint video image training on 16 frame video clips extracted from the videos of our dataset. All these are the variations which ended up with the best FVD. For dataset, we'll be using Moving MNIST dataset, where each video frame is of 72 x 128 dimension. And for simplifying, we'll only use easy videos for this dataset. We'll also train on 4 categories of videos from UCF dataset. And for UCF, we'll resize all the frames to 256 x 256. For both the datasets, we'll only train an unconditional generation model. So now looking at the code of everything involved in building this video model. The first thing we do is train an autoencoder, as we need to train diffusion model on latent videos. So for that, what we first do is extract frames from videos in our dataset in order to train the autoencoder. We have this capture frame script which gets the config file based on the dataset, and then this extract frames method is called. Here we read the config and get the dataset parameters. So this is how the config looks for MNIST. And these are the dataset parameters. And this is for UCF. There are a lot of parameters here, so rather than explaining them all at once, we'll talk about them as and when they appear in the code. Video path is the folder which has all the videos of our dataset. Image path is where we'll be storing the extracted frames. Then filter path. So this is a file which basically I have so that I can only take categories of videos that I desire. For Moving MNIST dataset, this will not exist because we are going to use all the videos. But for UCF, we are only going to work with certain categories. So this filter file is just going to keep the videos of interest. This is the video extension. Then we have this autoencoder frame sample probability. So since a lot of frames of videos might have similar spatial information, so it really does not make sense to train the autoencoder on the entire video. So here I just sample 10% of frames of the video and only use that for autoencoder training. Then we collect all the filters we need to use one by one. Fetch the videos matching each of those filters. And then for each video, we call this method, where we simply use OpenCV to get the video frames and save it in the image path location mentioned in the config. Then using these extracted frames, we'll train our VAE. We have two dataset classes. One is for VideoDataset for training diffusion model on latent videos, and this image dataset, which is for training autoencoder on images in pixel space. Let's look at the image dataset now. This gets the dataset config, and from that gets the height and width of images that you want to resize to. And if we want to do center cropping, this we are only going to use for UCF, as we'll resize and center crop UCF video frames to be 256 x 256. So it will be false for MNIST and true for UCF. Then based on image path, we get all the images and in get item, based on the config, we either do a resize and crop or just do a resize and return the image tensor after scaling it from -1 to 1. These are the only new aspects as far as autoencoder training is concerned. The VAE is exactly same as what we have been using in all the past diffusion videos, and even autoencoder training script is also same, using same perceptual and discriminator laws to get high quality reconstructions. If you're interested in also looking at VAE model architecture and autoencoder training code using these losses, then do take a look at the stable diffusion video where I have covered it in detail. For MNIST, we train a VAE with downsample factor of 4. So MNIST frames are 72 x 128 and we'll be getting 18 x 32 sized latents. And for UCF, we train one with a downsample factor of 8. Taking our images of 256 x 256 in pixel space to 32 x 32 x 4 latent images. And this is our result of autoencoder training. Perfect for the easy MNIST frames. For UCF, we could do better, but I've just trained it for 5 epochs, so the reconstructions should have more clarity with more epochs. You could also simply use the stable diffusion pre-trained VAE rather than training a VAE from scratch on your dataset. Now we'll look into training diffusion model on latent videos of our dataset. But before that, because I don't want to have both my VAE and diffusion model consume my GPU memory during diffusion training, I first use the trained VAE and compute and save the latent representations for all the videos in our dataset. That way, during diffusion model training, I don't have to use the VAE at all. So this save latent script exactly does that. In here, we instantiate our VAE model, load it with the trained checkpoint, then instantiate our video dataset. We'll look at this dataset class in detail next, but for now, just assume that it'll have a field video paths containing paths of all videos in the dataset. So for each of these videos, we read the video, either resize and center crop the video frames if we are working with UCF, or just resize in case of MNIST. Call our trained VAE model for each of these video frames, and ideally here I should also batch these calls rather than just using a batch size of 1, but it's fine. Then we save the mean and log variance computed by VAE. This is what the encode method here returns. So at the end of this script, we would have stored the mean and log variance for all the video frames in our dataset. Now this will consume a lot of disk space if we have very long videos. But since my GPU memory was limited and both my datasets have short videos, I did this. The repo also allows one to train diffusion model on videos without saving the latents. So if you have enough GPU memory, you don't need to do this step. Okay, now on to video dataset class. Here also we get this dataset config, and this latent path argument allows one to decide if the dataset returns pre-computed latents or frames of video. From the config, we now fetch few additional parameters. This number of images is used for joint video and image training, and basically is the number of randomly sampled frames that will attach to a video batch item. This is 8. And if we set it as 0, then that would mean we are doing video training and not joint video and image training. Number of frames is 16, as we'll be training on 16 frame video clips extracted from the videos in our dataset. This frame interval basically decides how the 16 frame clip is extracted. If we have a frame interval of 3, then that means we'll first extract 16 times 3, that is 48 continuous frames from a video, and then sample 16 equally spaced frames from it. For UCF, the authors used a value of 3, as that led to a decent level of continuity in the generated videos. But a lot of different values were experimented with, and ultimately all of them converge to similar performance. Frame height, width and channels and all the rest we have already seen. For transformations, depending on center square crop being needed or not, we'll either use resize and crop transform followed by normalization, or just resize followed by normalization. We should also have horizontal flip here, but I actually missed adding that here. Then load videos gets all the videos according to the filter specified. And if the latent path is passed, and that path contains the same number of stored latents as there are videos, we decide that the get item will return latents. Otherwise, get item will return video frames. So let's now jump to get item method. Here we'll do things differently if we are meant to return latents or return raw frames. Let's look at the latent part first. We load the latent file for this video item, extract 16 frames by first getting 2 random indexes that are 48 frames apart, and then 16 equally spaced frames are extracted between those indexes. Now for these 16 frames, using the saved mean and log variance, we get the 16 latent representations. Additionally, if we are in joint training mode, then for each image that we need to append to this video batch item, and by default we need 8 images. So in this loop, we get a random video latent, and then from that get a random latent frame. Then concat the 16 latent frames from the video clip and the 8 random latent frames together to get 24 latent frames for this batch item. For the else part, where we need to return raw frames, we do the same set of things, except rather than reading a latent file, we read the video, but post that similar set of steps. Also here we need to transform the images as well. For the latent case, these transformations were already taken care of in the save latent script. And finally, after all the steps, to extract 16 frames and 8 random images, we get our 24 frame batch item. With the video dataset done, now let's look at our latent diffusion transformer for video generation. So as I had mentioned earlier, we'll be working with variant 1, which will have alternate spatial and temporal layers, with each transformer block being the DIT block that we saw in our previous video. So this entire model initialization is exactly same as DIT, and the necessary parameters coming from config are also same as DIT. Even the layers are exactly like DIT. We have patch embedding, time step projection layers, transformer layers, unpatchify block, which has final layer norm, MLP to predict affine parameters, and final MLP to take the d-dimensional representation to patch height times patch width times channel dimensional representation. Each transformer layer is also same, having a layer norm for attention, followed by the attention module, layer norm for MLP, followed by MLP, and an additional MLP to predict the 6 sets of d-dimensional affine parameters. 4 scale and shift for both the layer norm, and 2 scaling parameters for post MLP and attention. If you want to dive deeper into the DIT implementation, then I get into that in my DIT video, but here we are only going to be looking at the forward method of our transformer, as that is the only difference. Our input will be the noisy latent frames, off-shape batch size, cross frames, cross latent channels, cross latent height, cross latent width. And we have time steps, which will be a 1D tensor with batch size values. We now have this additional argument called number of images, which is basically how many additional images have we appended in each batch video item. This will be non-zero only for joint training, and we'll see later where it's exactly used. But if we are in joint training mode, then the input will be of shape batch size, cross frames plus number of images, cross latent channels, cross height, cross width. For our patch embedding block, since we use uniform frame patch embedding, so we just rearrange the input to be batch size times frames, cross C cross H cross W. So basically embed the same way we embedded a batch of images in VIT or DIT. Inside the patch embedding block itself, we had our positional embedding added. So this output of shape batch size times frames cross patch tokens cross D will already have spatial position information added in it. We compute our time step representation So we'll have B time steps, B being the batch size. And after this time step embedding and projection layers, we'll get batch size cross D shaped representation for the time steps, where D is the hidden size of transformer. Now remember, when we are going to be working with spatial layers, we'll have batch size times frames cross patch tokens cross hidden size as input. But our time steps is batch size cross hidden size. To get time step representation for spatial layers, we replicate the first dimension to get a batch size times frames cross hidden size representation. And obviously for joint training, we'll have 16 plus 8 frames. So that's why we add number of images here as well. For similar reasons, because our temporal layers are also going to be working with an input of shape batch size times patch tokens cross frames cross hidden size, so we also create a time step representation for temporal layers by replicating the first dimension as many times as there are patch tokens to get a batch size times patches cross hidden size representation. Then we create our temporal embeddings, which is just sinusoidal embeddings for the first to last frames, so 16 values. Since temporal layers are only going to be working with 16 frames and not the additional appended random images, so we only have 16 values here, and the shape of frame embedding is 16 cross hidden size. Now we go through our transformer layers. In this loop, we extract pairs of consecutive layers. The first one will be responsible for spatial modeling and the second one for temporal modeling. At the start of our loop, the output is of shape batch size times number of frames plus number of images cross patch tokens cross hidden size, as we have already done a reshape prior to the patch embedding call. So now we call the spatial layer. Note that we have already added positional embeddings in the patch embedding block. If we did not do that, then we would have added positional embeddings here. Then we arrange the outputs to be of shape batch size times number of patch tokens cross number of frames plus number of images cross hidden size. Now because it's possible that we have appended random images that are not relevant to the video batch items, so we separate the video tokens from non-video tokens. So the first 16 frames are video tokens and the remaining 8 are image tokens. Temporal layers will not be impacting the image tokens. Then if this is the first temporal layer, we also need to add the temporal positional embeddings, which were the embeddings for the 16 frames. We pass the video tokens to the temporal layers, then concat the output video tokens with the output image tokens, which are unchanged. Post concatenating, we rearrange to have output to be of shape batch size times number of frames plus number of images cross patch tokens cross hidden size. And again note that spatial and temporal layers are exactly same, with only difference being the input shape. Then after we have looped over all the transformer layers, we call the final layer norm, modify that output using the affine parameter predictions done by the affine parameter MLP, and then final MLP to convert the hidden size representation to patch height times patch width times channels. And lastly rearrange to get batch size cross number of frames plus images cross channels cross H cross W. That's it for the video generation model code. And as you could see, the only differences from DIT was adding the temporal positional embeddings and rearranging the inputs differently based on whether the next layer is a spatial layer or a temporal layer. The training script is again exactly same as DIT training script. Get the config, get the noise scheduler, create the dataset, instantiate the model, Load the VAE if we are not going to use latents. And then in the training loop, get the frames or latents. And if we are working with raw frames, then additionally call VAE to compute the latents for these frames. And again for calling VAE, we rearrange and move the frame dimension inside the batch dimension. And after the VAE forward call, reshape it back to the original shape. Then sample random noise, time steps, add noise to the videos according to the time steps, and train our diffusion model to predict the noise using MSE loss. For sampling, again, everything same as image generation. The only difference being the shape of the random noise that we start with. We now start with a shape of 1 because we are only generating one video, cross 16, cross Z channels, cross latent frame height, cross latent frame width. Go through the reverse process. And after the 0th time step, we call the VAE to decode the generated latent video frames. And then save the generated video. That's it for the implementation. This is all the code that we need to train a diffusion model capable of generating videos. Once we train the model on MNIST easy videos for about 300 epochs, we get nice generation results. For UCF, it requires much more training epochs, and I kind of messed up with the configuration a bit, so I had to restart training all over again. And up till now, I've only been able to get these kind of results. Hopefully with more epochs, this will get better. But mind you, this is with the base model. And if we increase the model scale, it'll obviously lead to much better videos. I'll update the repo readme as well once I have better results for UCF. But do check out the repo for yourself and try to train a video generation model on your own video dataset of interest. Okay, so in this video, we built a model which generates 16 frame short clips. In upcoming videos on video generation, we are going to explore techniques which allows us to generate longer than 16 frame videos. And even see how to achieve text to video, video interpolations, converting images to video, and video editing. So see you then. And as always, thank you so much for watching these videos, and I hope you found this one helpful.